Okie dokie. So in this problem, we are going to be looking at a physics system that consists of a pulley, two blocks and a ramp, and friction. So we're adding friction into this normal system of two blocks being pulled over a pulley. So this is our diagram. As we look at this, we want to make sure we understand that M1 is representing the block that's actually on the ramp. M2 is perfectly vertical, so it's just hanging. We'll only have forces in that vertical direction. And then we have a 30-degree angle here. So when we get our forces, our free body diagrams drawn, when we get our sum of forces written, this will be the information that we are using. So for this problem, it says in the given figure that we just saw, M1, so this one up here, is 4 kilograms. The coefficient of static friction between the block and the ramp is 0.4. And so even just immediately knowing that we're in static friction, that's the only thing it's giving us, is that reminder that it's not going to move. And force static max, so that amount that we have to overcome is equal to mu s force normal. But if we don't actually get that, if we don't overcome it, then force of static friction is simply equal to that force applied. And force applied could be many different things. Maybe it's the tension, maybe it's the gravity. And so it's whatever is trying to create the motion. Force of static is simply just equal to that. So if we can, we overcome it, and that puts the object in motion, where you would use kinetic friction. So this is the maximum, what you're trying to overcome. If you do not hit this critical point, if you do not hit this maximum, then your force of static is simply equal to your force applied. So that's information that I want to go ahead and discuss before we even get started with the problem, because I know I'll be using that concept somewhere in this problem. It asks me to find the range of possible values of M2, so our block that is hanging, to find the possible range of masses for that, in which the system would be at equilibrium. So here at equilibrium, we know that that means the sum of forces would be equal to 0 in all directions. So it doesn't matter where you are, that sum of forces is going to be equal to 0. And so there's no acceleration. So that is what we're looking for when it's at equilibrium. So like any good forces problem, I'm going to start off by drawing some free body diagrams. So we have the box that's on the ramp. We know that we have tension. We know that we have force normal. We have, yes, some color coding here, gravity. And we know we have friction somewhere. Oops, I forgot to label my tension there. And we know that we have friction somewhere. So what we know about the movement here, if we come back to our diagram, we know that either the acceleration can be in this direction, that would mean that M2 is heavy enough that it is pulling this up the ramp. So that is one option. The other option then would be the acceleration down the ramp. And if the acceleration down the ramp, it is saying that M1 is heavy enough that it's pulling M2 up. Or M2 is light enough, since we know what M1 is. So those are the two different ranges that we're going to try to see, is how can we make sure that we're in this middle range where there's actually no acceleration. It's not in the positive direction or the negative direction. It is just none. And so that's going to affect our free body diagrams. So as I come back over here, I'm going to make the assumption first that the acceleration, if it were to occur, would be in the upwards direction. We know that our force of friction needs to oppose that. So we force of friction there. Now the reason why I was color coding is because we can immediately see that our tension and our force of friction are actually parallel to our acceleration vector. So they're already in the correct direction. Our force normal is perpendicular to that, so it's okay too. Force of gravity over here though, it's not in the parallel or perpendicular direction, so I need to break it down. And so those are going to be the two components. this is going to be mg sine theta, and this one will be mg cosine theta. And that's because our theta is nicely nestled right here. So whenever you're breaking down a ramp problem with our lovely properties of angles, because the angle was over here, when you do all of your lovely things, it ends up here. So once you've done that once, you can just go ahead and always do that. You don't have to work it out time and time again. That is where the theta goes. I can go ahead and write some sum of force equations for this box. And I'm going to use the same colors to do the direction, so in the parallel. So if we have tension going up the block, then I'm going to say tension is positive. So tension minus the force of friction would be equal to ma parallel. Immediately, we know that we're talking about a system that's at equilibrium, so that would be 0. So we would say tension is equal to the force of friction. We're looking at a system that looks like that. Because we're trying to find the range, whenever we're doing a problem like this, we're always going to be using that critical point of force of static. Too big of an eraser there. So we can then go ahead and say tension should be equal to mu s force normal. So that is what we are looking for here, is where tension is equal to mu s force normal. We can look at our perpendicular system, our direction, in which we're going to have, oh, I am so sorry. I did all of that and I missed a very, very key point, and I hope you guys caught me out on that. I color-coded on a reason. I forgot my mg sine theta. So let's go back and attempt this a little bit better. I was looking at this problem going, that looks too easy. Okay. So once again, tension is still going to be the positive, but it's going to be minus mg sine theta minus force of friction. So mg sine theta and force of friction are going to have the same sign here because they're both pointed in this downward direction. So we can say T is equal to mg sine theta plus force of friction, and we will still use that same last idea. So tension is equal to mg sine theta plus mu s force normal. Now we can go ahead and do our perpendicular. Once again, a system at equilibrium, so perfectly equals 0. So we can go ahead and immediately say force normal is equal to mg cosine of theta. Now, through all of this, we're trying to find M2. And obviously at this point, I don't have M2 in here. All of these should be M1s. I've been really, really consistent in my writing. And so I've found everything I can from this first box, but obviously it's not enough. So now I need to go ahead and look at my second box. So the second box is just would be moving down in this case. So the acceleration vector would look like this. So if this one's moving up the ramp, this one would be moving down the ramp. We have force of gravity, and we have tension. So that makes it very easy for us. We can simply say that our force of gravity minus our tension would equal ma in that y direction. Once again, we are at equilibrium, so we're saying that would be equal to 0. So force of gravity is simply equal to tension. So m2g is equal to tension. Well, the cool thing here is now we have tension here and we have tension here, so we can go ahead and set these equal to each other to figure out what is M2. Here, once again, I solved for force normal, so I need to make sure that I'm putting that in. Each of these terms have a g in it, so m2 is equal to m1 sine theta plus mu s m1 cosine theta. And that was just a mistake here, and get over, once again, force normal was mg cosine theta. So when I set this in for force normal, it's admit m1 g cosine theta. So just made that correction really quickly. And at this point, it's just putting in our values. And I factored that M1 out to the front. So let's go ahead and put this into our calculators. And this is always a good reminder to make sure that your calculator is in the correct mode. So here, obviously, we're dealing with degrees. So always a good thing to go back and double check that your calculator is actually in degrees. And at this point, you should get M2 is equal to 3.39 kilograms. So looking at that, we were looking at what would be the maximum possible value, because we're saying here if the acceleration is moving up, we're saying M2 is heavy enough that it's moving this. So we're trying to find what would be that critical value of M2. And so as soon as M2 is greater than this value, it's going to start pulling M1 up. It's going to overcome that force of static. But as long as it's less than that, we're good to go. So that's going to be one of our ranges. Is we're going to go up here and say M2 has to be less than 3.39 kilograms. So we just did all of that work in the assumption that our A was going up. But if we come back, and we're going to erase some of this because we're going to slowly change it and say what happens if we switch that acceleration vector. And I'm going to go ahead and switch its color so we know we're doing something different here. Now we're going to say what would happen if that acceleration was going down. So over here, that would mean that the acceleration is going up. So some of these things are going to stay the same. Some of these things are going to change. The biggest thing here that is going to change is that if my acceleration is now going down, that's going to change the direction of my force of gravity. I said force of gravity, but I meant force of friction. And we can see that from what I had erased. So we know that our friction opposes that possible movement, and static, so I'm saying possible movement. And so here we would be in the case where this block is trying to move down. So that would be the possible movement. So the force of friction will be pointing up the ramp. So now as I write my sum of force equations, I'm going to have tension plus the force of friction, because they're in the same direction, minus mg sine theta this time. So the tension stayed in the same direction, and here mg sine theta is going in the other direction. So making sure that tension and force of friction have the same sign because they're going in the same direction, and then mg sine theta has the opposite sign. Some of you guys may have wanted to go ahead. Something that I do often is making sure, oops, that's way too big of an eraser. I often like to make sure that my positive is in the same direction as that possible acceleration. So I could have made these two negative and this one positive. Because this is equal to 0, that doesn't matter. Either way you do it, we get to the statement that mg sine theta is equal to tension plus force of friction. So because our acceleration is actually 0, it doesn't really matter which one you make positive and which one you make negative. It's just extremely imperative that tension and force of friction have the same sign. Mg sine theta has the opposing sign. That gets you to the statement here. But if we think about it, we go, hey, we know that we're eventually going to need tension by itself. So we're really going to say that tension is equal to m1g sine theta minus that force of friction. So that's what our tension is going to be equal to. And we know that we need tension by itself because when we get over here, when we start talking about this one, because it's what we're solving for, we know that we're going to need to isolate tension. So that was that step here. We can go ahead if we want to keep taking this further. Tension equals m1g sine theta minus mu s force normal. That means that we need to go in and find our force normal. By switching the force of direction, by switching the direction of the force of friction, we didn't change anything here. So I can go ahead and say that force normal is still going to be equal to mg cosine theta, and that's because they're still the only two forces in this direction. So we're good to go. As I come over here and look at this one, we're still just going to have m2g is equal to tension. That didn't change because even though this direction changed, it's technically zero. These are the only two forces. There's no acceleration, so they must be equal to each other. We're now ready to go ahead and keep solving. I don't know why I put two parentheses there. Okay, so you notice that the only thing that is truly different here is that this became a minus sign. We had to do all this work to show that, but otherwise it's the same type of math. So we're going to cancel those g's out. We get m2 is equal to m1 times sine theta minus mu s cosine theta. And now we can go ahead and solve this one. So we get m2 being 0.61 kilograms. If we go back up and talk about what we were talking about here, we were saying what would happen if the acceleration was in this direction. So we're saying that this would be so light that we could actually pull it down. And so that is the heaviest it could be. If it was any lighter than 0.61, we would tip the scales. We'd no longer have zero acceleration. We'd have enough force to overcome that static, and it would go ahead and pull it down. So if we add that to our statement, and this would be our final answer here. So we were looking at that magical realm where there would be zero acceleration. We found it by saying what would be that force, or sorry, what would be that mass that would make this one light enough that we could pull it down. So lighter than this, and it's going to start moving. We also did the opposite of what mass does this need to be? How heavy does it need to be to be able to pull the block up the ramp? And that would be that critical point. So M2 needs to be between these in order to get there. So here you saw that it was really important to draw your free body diagrams to determine where's your acceleration pointing. Be very careful with your positives and your negatives, with your labeling of your M1s. We have a free body diagram for both blocks. We knew that the only thing they had in common here was that tension. Acceleration is typically the other thing they have in common, but we're talking about that equilibrium, so they were zero. And there you have it. I really like this problem. It really makes you think critically. And with that, I actually think there is a part B, which is a really good reminder of this here. So part B just says in the given figure, so we're using the same exact thing. It says find the frictional force on the M1 block if M2 equals 1 kilogram. Well, the very first thing you need to recognize is that 1 kilogram falls into this range. 1 kilogram falls into this range of it is perfectly at equilibrium. So it's not being pulled down, it's not being pulled up, it is at equilibrium here. So with that being said, we have some different things that we can look at here. So if this is M2G, we can immediately go ahead. We know that M2G is going to be equal to tension. That isn't changing. So M2 was 1. So 1 times 9.81 is equal to our tension. So our tension force is equal to 9.81 newtons. If we come over here, we need to figure out how that plays into effect because we're talking about M1. We're trying to figure out where it is, what's going on. The fact that M2 hasn't changed, M1 hasn't changed, it's still 4 kilograms. So we can go ahead, we know here the biggest thing is that our force of friction has to be equal to that applied force in this case. And so we need to compare which one is larger to really try and figure out what's going on here. So we need to figure out which direction our force of friction is pointing. And so if we do this out, we know that the two forces that could either be pulling on it are mg sine theta or tension. Well, we know that our tension then is equal to 9.81 newtons. And if we do this out with our 4 kilograms, we actually find out that our mg sine theta is 19.62. So since our force of gravity, the component that's pulling it down the ramp, is higher, that means that our force of friction is actually in this direction. Because it has to equal that out. We have to make sure that we have 0 force in this direction because it's at equilibrium. So this one is larger, which means force of friction has to be helping out here. So we can then say that tension plus the force of friction is equal to 19.62. This was 9.8. And we find out that our force of friction is equal to 9.81 as well. So the reason why I want to make sure we do this is so many people just want to immediately say, oh, I can just still use that mu s. I know I'm in that equilibrium area, so I can just say that my force of friction is that critical point because we didn't hit it. But we know that's not actually true. It's if you haven't hit your critical point, it's really just whatever equals out where that motion would be. So once again, we knew that there were 0 forces here. We knew that there was absolutely 0 net force in this direction because we're in the equilibrium. And so I had to do a little bit of comparing. You could have probably just done this by doing a sum of forces and setting them all equal and then analyzing what your negative versus your positive would mean. I like to immediately know what direction it's going in. And so I immediately said, okay, the only things that could be causing it to move would either be the tension or this component of the gravity. I went ahead and put the values in to figure out which one was bigger. Because the gravity that's pulling it down the ramp was larger than the tension that was holding it in place, I know that this block is trying to move in this direction. However, there is 0 acceleration, so that force of friction had to help cancel it out. So whenever you're dealing with static friction, realize that you're really just, it's the amount of friction needed to cancel out the movement. So there wants to be acceleration, that force of friction is bringing that back to 0. And so there you have it, a nice problem that deals with inclines, it dealt with tension, and it dealt with static friction.